Math 2414, trigonometric integrals, integrating a product of secants in or tangents, part 3. At the end of the last video, I said in this video, I just want to show you 2 specific examples. Actually, it's 3. But they're all small integrals, and they're ones that don't quite follow these rules. So let's see what happens. Let's start with this integral of secant x dx. Well, it's just a secant to an odd power, so it doesn't fit here. I'll be honest, I don't know how the person who first said do it this way saw to do it. Maybe they were observational, they grabbed some things that didn't look like they put together, but they did. I'll show you what the answer is, but I'll show you where it comes from. This is one that you pretty much want to have memorized, but I am going to show you where it comes from. The integral of secant x is the natural log of the absolute value of secant x plus tangent x plus c. Not a standard integral by any means. How do you possibly get from here to here? I'm going to show you that in a second, but this is one that you should just add to your list of integral rules. The integral of secant x dx equals the natural log of secant x plus tangent x plus constant. Why? A very dirty trick, but it's one that has some merit on a general level as opposed to this specific example. The dirty trick is to think of this as a fraction and multiply both sides by the same thing. That's always a move that's at your disposal anytime you're dealing with anything in calculus or algebra and trigonometry. You can always think of something as a fraction and multiply both sides by the same thing as long as that thing's not equal to 0. So what magical thing would we multiply by? Secant x tangent x. Excuse me, secant x plus tangent x. Now why on earth is that a good idea? Well, watch what happens if we distribute across the top. If we distribute across the top, we get secant squared x, which is the derivative of tangent, plus secant x tangent x, which is the derivative of secant. And in the bottom, we pick up secant x plus tangent x. Again, I'm not asking you to memorize how to get this answer. I'm just showing you where it comes from. I want you to know the answer to this integral is this. So where does this get us besides making it look like a total mess? Well, a nice little substitution is to let u equal the denominator. Let u equal secant x plus tangent x. Because remember what I said as I was writing the numerator? That this is the derivative of tangent and this is the derivative of secant. Well, the derivative of secant is secant x tangent x. The derivative of tangent is secant squared x. So du is all that dx, which means if we did a substitution, everything up here becomes du, this becomes u, this becomes the integral of 1 over u du, which is the natural log of the absolute value of u, but u is equal to this, and that's why the answer is what it is. Again, who or how did somebody have the foresight to say, hey, let me break out this fraction out of apparently nowhere? Well, maybe they had the observation that the derivatives of these were the same, except one has this extra secant and one has an extra tangent. So that's where it came from. And again, in my class, I'm not going to hold you responsible for replicating how to integrate secant of x. I was just showing you why its answer is what it is. Then again, we could have just taken the derivative of the answer and then shown it equals the integrand, but that was the technique. So that's example number 1. The integral of secant x dx equals the natural log of secant x plus tangent x. Integral number 2 I want to show you is the integral of tangent squared, which does not fit. Well, it sort of fits. The power on the secant is even because there are no secants. Secant to the 0 power, but the power on the tangent is not odd, so we can't use this. So if we did this, our substitution would apparently be u equals tangent x, but there's a problem immediately with saying let u equal tangent x. Then du is secant squared x. There's not a single secant in sight. Or is there? The dirty trick for integrating tangent squared is to change it to 1 minus secant squared x. Oh, look. If we integrate this term by term, the integral of 1 is just x minus, well, if the derivative of tangent is secant squared, then isn't the integral of secant squared tangent? That almost seemed too easy. And I'm beginning to second guess myself, but I'm not. Yeah, the trick to this one is to change tangent squared to 1 minus secant squared. And you can file this under integration rules because it's a very specific example. Integral of tangent squared equals x minus tangent x. And you can check it real quick by taking the derivative. Derivative of x is 1, derivative of tangent squared is tangent is secant squared. This disappears, 1 minus secant squared is tangent squared. That's not right. Oh my gosh. I could start the video over, but I don't mind people seeing me fail and make silly mistakes. Because I'll say it, I said it before and I'll say it again. I don't care how good you are. Everybody makes careless mistakes. I see people on YouTube putting math videos of higher level math context. I watch a lot of them because they're good, with thousands and millions of views, and I see them make mistakes. And people call them out for it, and they usually go back and say, oops, but it happens. I don't care how good you are. Tangent squared is not 1 minus secant squared. Tangent squared is secant squared minus 1. It doesn't really change anything except the order. So it's tangent of x minus x plus c. Derivative is secant squared minus 1, which of course is tangent squared. So you can file this under just integration rules that the integral of tangent squared is tangent minus x. But that's how that integral is calculated, by changing tangent squared to secant squared minus 1. And really, it's kind of driven by this. There were no secants. Secant to the 0 power 0 is even, so we used a substitution of tangent, but we had to create the secant squareds for the du package by using this trig. So you know what? I take that back. It completely falls under this. It's just very stealthy because this even power is 0. Now, the one that doesn't fit nicely under either of these and is not obvious and is a classical integration problem, that usually means it's on a test, not always, is the integral of secant cubed. Well, how can we integrate this? Let's think about it. I know how it's going to go. I'm just trying to naturally motivate it, not just put it up there and say, do this, because I know it's going to work. A lot of good that does you. Well, we can do this, but why don't we try, and this actually points out something interesting. When you're doing a trig integral, if you don't have a strategy, just try something. So what can we do with secants? Well, we can change secants to tangents if we got 2 of them. So let's try that. Let's try peeling off 2 of the secants. Actually, by writing it like that, it's product. And I know I've repeatedly said, we don't integrate products, we integrate sums and differences. I'm sorry, I normally wouldn't get a bite of my snack during a video, but I keep forgetting to get a bite between videos. So I'm going to go ahead and have a bite of my Buc-ee's sweet and savory. I'm not getting any kickbacks, but it's some good snackbacks. Anyway, so this is a product. Sorry, this is a product. And normally we don't integrate products, but there's no way to make it not a product here. Can't distribute away parentheses. But wasn't integration by parts a technique for handling an integral of a product? It was. So in an unconventional move, I'm going to try this trig integral by doing integration by parts, which I've abbreviated IBP. Now, if we're going to do integration by parts, we need to pick a u and a dv. But remember, the u gets differentiated, the dv gets integrated. So of these 2 parts, which one is more easily integrable? Well, we know the answer to both of them. Which one is a prettier answer as an integral? Well, we just integrated that one previously as the natural log of absolute value, secant x plus tangent x. Oh, by the way, we should probably remember how integration by parts works. The integral of u dv is equal to uv minus the integral as a u and a dv, create the v, create the du, build this, and then cross our fingers and hope for the best. All right, so both of these are integrable, but whichever one I integrate, the v is going to land up there, and I'm going to have to integrate it again. If I call this dv, in other words, if I say dv is equal to secant of x dx, then v is going to be natural log absolute value of secant x plus tangent x from the first video in this, from the first integral in this video. And I'm not looking forward to parking that inside of an integral. So maybe that's the bad choice for dv. Maybe dv should be secant squared. Oh, wait a minute. That's just the derivative of tangent, so v is equal to tangent x. I'm not too worried about putting that in there. But if dv is secant squared x, then u is secant of x, which means du is secant x tangent x dx. All right, well, at least there's no natural logs. So let's set up integration by parts using this, this particular setup. This integral is equal to u times v, so secant times tangent. That's not too bad, it's not getting integrated, it's just sitting up there. Minus the integral of v du. So minus the integral of tangent times all this. Tangent times tangent will give me tangent squared. And then a secant. And then dx. Okay, that's not too bad. And again, integration by parts doesn't do an integral, it just changes it. But let's see if we can do this integral using one of these. If q is even, if the power on the secant is even, it is not. The power on the secant is 1. If the p is odd, if the power on the tangent is odd, it's not. All right, so we change it from one integral that we can't do into another integral that we can't do. But I'm not giving up yet, because we're integrating trig functions. And anytime you're doing calculus with trig, all trig is fair game, namely all identities. That's empty. Well, I guess I could call tangent squared secant squared minus 1. You know, I'm feigning like I don't know if it's going to work or not, and I know it's going to work. But when you're doing an integral and you don't have a clear path, you just try something and hope for the best. I can change tangent squared to secant squared minus 1. That had a secant on the outside of it. Well, let's distribute this. Actually, let's do two things. Let's distribute the secant to get secant cubed minus secant, and distribute the negative and set up two integrals. So for this secant, it's going to be minus, and then a secant cubed. Minus integral of secant cubed x dx, excuse me, secant cubed. And then for this, it's going to become plus the integral of secant. Oh, I know that integral. Well, where are we? Well, I can do this integral, but I can't, wait a minute, this is the one I'm trying to do. Dagnabbit, I'm right back where I started. Wait, this is the recursive scenario for integration by parts. I forget the video number, but go back to the integration by part video series and watch someone that says recursive scenario. Let me bring this guy down. Integral of secant cubed x dx is equal to secant x tangent x minus the integral of secant cubed x dx plus the integral of secant x dx. Well, I know this integral. This integral is the natural log of the absolute value of secant x plus tangent x. It was the first integral we discussed in this video. And in the recursive case of integration by parts, what happens is the integral you are solving for shows up on the other side. And hopefully it doesn't match exactly, otherwise it would cancel. And since they don't match exactly, I can solve for this by adding the integral of secant cubed x dx to both sides. Let's get rid of that and give me two of these integrals is equal to all this, secant x tangent x minus, plus natural log absolute value of secant x plus tangent x. And And now all I have to do is multiply everything by half, or equivalently put everything over 2. And being an indefinite integral, constant of integration. I don't expect you to have that answer memorized, but I wanted to demonstrate that integration by parts is always an option if you can look at your integral as a product, which this is secant cubed. It's a bunch of secants multiplied together. And when you do integration by parts, the idea is to turn it into something that you can finish. In this case, we turned it into something, and then for whatever reason, we decided to change tangent squared to secant squared minus 1. And as a consequence, we got the same integral on the other side. And so it was the recursive scenario for integration by parts. It is common for calculus professors to ask a question like this on a test, where you just have to know that the move is to do integration by parts in one move, create the recursive scenario, which is different than last time. It was 2 moves that created it. So am I going to do that? I don't know. I got a lot of fish to fry on my test. I don't know if this is going to be one of them. But I just wanted to demonstrate the integral of secant cubed because it is a non-standard integral when it comes to trig integrals.